In this video, we're going to show you how to find the mean and the variance of the hypergeometric probability distribution function. So just before we actually get into that one, I'd like to contrast the binomial probability distribution to that of the hypergeometric probability distribution. Perhaps in another video I will show you how under certain assumptions the binomial probability distribution is the limiting distribution of the hypergeometric distribution. So first of all, if you recall, a binomial experiment was an experiment where we had n independent trials. Each trial was Bernoulli, and the probability of success was fixed and remained fixed from trial to trial. Okay, and the key is that the key assumption for the binomial distribution function was also the fact that the sampling is done with replacement. Although in practice, most likely we do not do that, we just sample without replacement. So for example, if I'm choosing 5 registered voters from a population, I'm just going to select them by some means of random selection. But I'm not going to put them back, the individual that I select, I'm not going to put them back in the pool of registered voters and give that person another opportunity to be selected. Now, if we sample from a finite population and the ratio of sample to population size is not less than 5%, then the probability of selections actually change. So it's not that fixed probability that we assumed it to be in our first assumption, right? The probability of success is fixed. That assumption is going to be invalid. Therefore, we come into a more realistic probability distribution that will address those deficiencies, or I should say those modifications. So what is a hypergeometric experiment? Well, the hypergeometric experiment, again, kind of like the binomial, we have certain restrictions on it. First, the outcomes are Bernoulli, success failure kind of outcomes, and again, the success failure may not have its usual connotation in that, for example, a success may be to get a flat tire. Sure, that's not really a good thing to have as you drive. Or success could be the incident of having some kind of a terminal disease. So just as a general notation, we call these success failure. And there are n trials. These trials are not independent. Notice the sharp contrast to the binomial. The trials are not independent. And the fact that number 4, sampling is done without replacement, that means the probability of success is not going to be fixed from trial to trial. And finally, we assume that the ratio of sample to population size is bigger than 5%, so that we cannot use the binomial approximation. Okay, now the term hypergeometric, like where does that name come from? What does it mean? Well, it has to do with hypergeometric series or hypergeometric function. The hypergeometric distribution in probability is indeed a special case of a more general series called hypergeometric series, and the series in the 19th century were studied by Euler and Gauss, but I believe it was in 16th century, maybe 17th century, Wallace actually studied it also. In fact, I think he was the one who proposed them. But these are very versatile series, and they're very interesting. A bunch of other series are derived from this series, and even other probability distributions emerge from this hypergeometric series. Again, very, very useful series, and it's not one that you typically encounter. But anyhow, this is what the general hypergeometric series actually looks like. I just thought I put that on there so you kind of see it. Now, I have written out the series here. expanded it. So you see the first few terms of the series. Notice when n is 0, you actually start with 1. Okay. So the pattern in the fraction begins actually with n equal 1. And so when n is 0, indeed, you get x to 0 over 0 factorial, which is 1. And we take all of the fraction to be 1. Okay, that's just by definition. Now, you have the second, third, and so on of the series here. Now, if I let a be 1, b and c let them be equal, then I can rewrite the series in this form, right? And crossing out the common factors, notice I replaced the denominator. I replaced it by, instead of c, I replaced it by b, so hence the cancellation. And then you work this out and you get something very simple, right? X to the n, and I'm sure all of you recognize this one as famous geometric series, right? The common ratio is x. True? So notice, I just want to point out other series could emerge from this, and so does, in fact, the hypergeometric probability distribution that you're about to see. That too emerges from this series. Okay. Now, the hypergeometric probability distribution is given by this. Remember the hypergeometric experiment, I defined it above. So this is just the hypergeometric distribution. Now, this is the function f, the random variable is x, and we have in the numerator we have k choose x times n minus k, capital N that is, minus k over little n minus x, choose little n minus x, and in the denominator we have capital N choose little n. Now in this notation, what are these? Actually, the capital N here is the population size. Okay, and maybe I should write these down for you. Let me write this down. So in that form that I have, we're gonna let the following, we're gonna call n to be the size of the population. So that is our population size. Little n, of course, is the size of the sample or number of trials, right? This would be the sample size, and in this notation also the capital K here is actually the number of successes in the population. I'm going to call that number of successes in the population. Okay, and then let's see what else we had. Oh, we had little x, right? The little x would be the number of successes, of course, in the sample. Okay, let me write that. Number of successes in the sample. Okay, and there we have it. So we have capital K, capital N, little n, and little x. Okay, so we have all of those down. Now, what we'd like to do is actually be able to derive the formulas for the mean and the variance of a hypergeometric distribution. But somewhere along the line, in order to be able to do that for the mean, let me actually do this. I want to show you this thing because I'm going to need this in finding the mean of the hypergeometric distribution. Let's begin with an observation here. Okay, let's say I'm multiplying 1 plus x to the n times let's go 1 plus x to the k. So suppose I'm multiplying those two binomials. Now, of course, the multiplication from algebra, that's pretty easy, right? You combine the exponents, right? Now, let's actually write out each of these binomials using the binomial theorem. So the expansion of 1 plus x to the n is going to be, if you recall, I'm going to put that in a bracket. Okay, so it's going to be 1 to the n, right, plus n choose 1, and then 1 to the n minus 1x, plus n choose 2, 1 to the n minus 2 x squared, and so on, right? That's just straight expansion all the way to the n, which we can write it as simply x to the n, or a little fancier, n choose n times x to the n to maintain the pattern in the binomial coefficient. Okay, then we're going to multiply this by the second binomial is 1 plus x to the k, right? So for this one, it's going to be 1 to the k, and of course that's 1 just as 1 to the n is in the beginning. So that's just 1 to the k plus this time we're going to go, it's going to be, let's see, I'm going to be k choose 1, right? 1 to the k minus 1, and then we multiply by x plus k choose 2, 1 to the k minus 2, and then k squared, and all the way up to the last one is going to be what? K choose k, right, times x to the k. So that's just the product of the two binomials. Okay, and of course we can use distributive property, and we can distribute each and every one of the first binomial to each and every one of the second binomial expansions, right? Because there are n plus 1 terms in the expansion of 1 plus x to the n, and k plus 1 terms in the expansion of 1 plus x to the k. So in all, if you multiply, we're going to have what? N plus 1 times k plus 1 terms are actually in the expansion, right? If we were to multiply them out, but we're not going to, right? In expansion. Now, what I want to do, however, is this. Let's say I'm going to look at the first few terms of this product. Okay, so in other words, I'm going to multiply 1 times 1 here. So we're going to get 1. That's the first term in the expansion, right? The very last term in the expansion, of course, is when you do the last terms. So the very last term in the expansion is going to be x to the n and times x to the k, which is x to the n plus k, right? Okay. Now, what about the second term when we multiply here? So let's say I multiply 1 to the n times the second term in the binomial, right? And that will give me a coefficient on x. And when I multiply the second term in the first expansion by first term in the second expansion, then I also get the coefficient on x, right? So in other words, what I want to do is find the coefficient on x. So the coefficient on x turns out to be itself, use a bracket here. It's going to be what? It's going to be simply n choose 1, right? 1 to any power is 1, right? So I'm dropping all the 1 to the powers, be it n minus 1, n minus 2, doesn't matter. And the second expansion, all of the 1 to the power of k or variations of it are going to be 1. So I'm just going to drop those. Okay. So the coefficient on x is going to be, again, that's when I multiply 1 times that, and when I multiply the second term in the first expansion by 1 in the second expansion. So it's going to be n choose 1 x, right? Well, actually, let me factor the x, plus k choose 1 times x. Okay, and that's what that's going to be. Right? Pretty simple. Now, what about x squared? How am I going to get x squared? Let's try the same thing. To get x squared, I can multiply 1 times x squared here. Ooh, hold on. This is not k, sorry. That should be x squared. Okay. I'm sure most of you caught that. I was just oversighting it. All right. So how do I get x squared? That's when I multiply first term times the x squared term in the second expansion, or multiply first term in the second expansion times the x squared term in the first. Also, when I multiply x times x now, right, I get x squared. Now, putting all of this together, the coefficient on x squared is therefore going to be, it's going to be n choose 1, right? N choose 1 times k choose 1, right? That's this distribution. And the other way to do it was to do it plus n choose 1 time I already wrote that. Okay. I was looking at this one, the one I just did. I don't want to do that again. Or I can do n choose 2, right? And also plus k choose 2, right? Those are the coefficients on x squared, plus so on and so forth, all the way up to the n. The last product is going to be x to the n plus k. All right. Now, my focus will be on just the terms, the x terms and x squared terms. Okay. Now, if I let me put this on hold now. Okay. In fact, so that's how that's going to look like. Remember, there's going to be quite a few terms in that expansion. Now, let's put that on hold and actually take a look at the expansion of 1 plus x to the n plus k. Okay, so 1 plus x to the n plus k. Now that expansion, what is that going to look like, right? Well, that expansion is going to be 1 to the n plus k plus, and then we go down the factorial patterns. It's going to be n plus k choose 1, 1 to the n plus k minus 1, and then you have, of course, x, just x, and then so on and so forth. N plus k choose 2. I'm going to drop the 1 to the power and just keep the x squares and the powers on x. And plus the last term, of course, is going to be x to the n plus k, right? That's the right side. And if you look at the last terms and look at the first terms, of course, they're the same, right? So now let's take a look at the coefficient on x term, right? The coefficient on x term. And then we're going to look at x squared and then make a generalization here. So the coefficient on x, remember, this is just 1, so you don't need to write it. We're looking at these two versus the one in the expansion of 1 plus x to the n plus k. So n choose 1 is just n, right? And k choose 1 would be k. Now n plus k choose 1 is going to be n plus k. So if you look at, if I equate, in other words, the coefficient on x, the coefficient on x is going to be n1 plus k1, and that turns out to be equal n plus k choose 1, right? We just showed that in effect, right? This is n plus k, and the other side is also n plus k. So it checks. Okay. And then let's do this. Let's equate the coefficient on x squared. Now, this is the coefficient on x squared, right? Let me write that into K2 and 1 K1. Okay. So that the coefficient on x squared is going to be, from the first expansion, is going to be n1 K1 plus n choose 2 plus k choose 2, right? Now if I look at the coefficient on x squared, and here that's n choose k, n plus k choose 2. And those should be equal. And we'll verify it, right? So again, n choose 1 means n, k choose 1 is k. N choose 2 is n factorial, 2 factorial, n minus 2 factorial, plus k choose 2 likewise, k factorial over 2 factorial, k minus 2 factorial. And let me start from here, nk plus the middle fraction, I'm going to go n minus 1, n minus 2 factorial, divided by 2 factorial, n minus 2 factorial, plus the last fraction, k factorial, I'm going to go k minus 1, k minus 2 factorial, and then divide by 2 factorial, and k minus 2 factorial. And on the right side, put question mark because we are verifying it. The right side, the n plus k choose 2, that means n plus k factorial over 2 factorial, n plus k minus 2 factorial, right? That's just by definition of binomial coefficient, what n choose k meant. Okay, now let's cross some things out here. Those cross out, these cross out. So what do we have left over? We have nk plus nn minus 1 over 2 plus kk minus 1 over 2 equals. Now n plus k factorial, I'm going to write that as n plus k, then n plus k minus 1, n plus k minus 2 factorial it, divided by 2, and then n minus k minus 2, or I'm sorry, n plus k, not minus, it's going to be plus k minus 2 factorial. Okay, and I can cross those out. Now what else can I do? Well, on the left side, let's combine those fractions. The LCD is 2, so I get 2nk plus n squared minus n plus k squared minus k, and on the right side I'm just going to get n plus k minus 1 divided by 2. I'll keep the right side the way it is. Okay. You could expand it, you know, multiply it out, whatever, but I'm going to keep them separate. Okay, and then what do we do? Oh, hold on. Yeah, that is k. Let me move this away so it doesn't look like k squared. It just threw me off. It may throw you off too. And this one. All right. Now, the first fractions numerator. Okay, I have 2 nk's, right? So I'm going to write that as the following. First, I'm going to write it in descending powers of n squared minus n plus nk. Okay, so I'm going to spend, I have 2 nk's to spend. This is how I want to spend one of them. Plus, then I have k squared minus k plus nk. That's my second nk. Remember, I have 2. I can spend it however I like. That's how I want to do that one. So I split 2nk into nk plus nk divided by 2. Now, let's see. First, trinomial. I'm going to factor the n here. So I get n plus k minus 1. And factor k from the second one. I get k plus n minus 1. All of that divided by 2. Okay, now if you look at the trinomials. Those two are the same, right? Except K and N are swapped out, but they're the same trinomials. So I'm going to factor the GCF. So if I factor the GCF now, that's n plus k minus 1. All that remains is n and k. So I'm just going to have n plus k divided by 2. True? Now, if you look at what is up here, that's exactly what's down here, right? Remember, this was the right side once we multiplied the two binomials together. Okay, so now the reason I went through all of this, right, we did all of this, is to make the following observation. Therefore, you can do this for coefficient on x cubed, coefficient on x to the 4th, all the way to coefficient x to the n. So this is now the generalization. So I'm just going to say, let's call this the generalization of what we just observed. If we generalize this, then we can say this is when we equate coefficients of x to the n. Okay, these are the coefficients of x to the n. We can write it at the sum of j0 to n of a choose j, b n minus j, and that would equal to a plus b choose n. That's what we just showed. Okay, and there you have it. So for example, for the case where n is 1, just to see how this is going to work out. So this is what I wanted to arrive at, the generalization of that series. So for example, when n is 1, okay, when n is 1, the sum j0 to 1 of a choose j, b choose n minus j becomes that's going to be a choose 0, j is 0 now, b choose n is 1, right? B choose 1 plus j is going to be 1 next time around, and remember n is 1, 1 minus 1 is 0. Okay, b 0, and this is going to be a choose 0 is 1, b choose 1 is b, a choose 1 is a, b choose 0 is 1. So this is going to be simply a plus b, right? And will that equal to, what I'm proposing is a plus b choose 1 in this case. That would equal to a plus b choose 1 is just a plus b. So it checks. So there you have it. It works. We just showed the right left sides are the same. You can do the same thing for higher n values. Okay, now why are we doing this? Okay, so let's actually now try to find the expected value or the mean of a hypergeometric distribution. Okay, let's do that. Okay, let me go back and look at the parameterization of my distribution. Okay, so I'm using k in here. Okay, doesn't matter as long as we're consistent with our choice of letters. All right, so here we go. We're talking about the mean of hypergeometric probability distribution, or mean of random variable x, right? Now by definition of mean, therefore we're going to call mean of random variable x is expected value of the random variable, right? So in the case of a discrete, that means we're going to go x equals 0 to n, right, of x, and then we go k choose x, well, let me write this. It's going to be x times f of x. That's what that is, right? So I'm just following the definition of expectation. All right. And so that's going to be x times, and then we have k choose x, and then capital N minus k over n minus x choose n, right? So that's what we have. Now, here's what I'm going to do. Okay, let's see. A lot of magical moments gonna happen here. Okay, so first I'm going to actually bring the m and an m, little n, and a capital N out here. Okay, and how is that going to be possible? Is if you look at the denominator and choose n. Okay, remember we can write it as n minus 1 factorial, and then n factorial n minus n, right? Factorial. And I can actually now pull the, let me write it one more step. So I want to keep that as n minus 1 factorial. And then the little n factorial is n minus 1 factorial. And then n minus n factorial, I'm going to write that as n minus 1 minus n minus 1 factorial. Okay, now why do we want to do that? Because now I can pull out a capital N, a little n, and the remaining expression is indeed a rewrite of n minus 1, choose little n minus 1. Okay, so that's what that is. And because it's in the denominator of my summation, so when you bring it to the front, you can invert and multiply it, right? You can flip and multiply it. Sorry, this should be, there you go. So that's where this, take it step by step, that's where this little n over capital N comes. It comes from that denominator. Okay. Now in the numerator, where I have k choose x. Okay, let's take a look at that one. Likewise, I can write k choose x as k factorial over x factorial k minus x factorial. That's by definition of the notation. And I'm going to actually write this as k over x. That's going to be k minus 1 factorial, right? Because k factorial is k minus 1 factorial. And x factorial is x minus 1 factorial, right? Minus 1 factorial. And then, of course, k minus x, again, like I did above, I can write that as k minus 1 factorial, I'm sorry, not factorial, but simply k minus 1 minus x minus 1, and then factorial it. And this way I can bring the k over x out, and what's left over is going to be actually k minus 1, x minus 1. Okay, so I'm gonna do that now. That means I'm able to bring k in front. Okay, now therefore my sigma is going to be x0 to n. And remember, there's an x that multiplies by the fraction. So it's going to be x times, in the numerator is going to be the k choose x. I'm going to rewrite it as k minus 1 choose x minus 1 now. K minus 1 choose x minus 1, right? And the latter part isn't going to change. That's just going to be n minus K-N minus x. This part didn't do anything to that. Now remember, when I did this work, I have k over x, right? So where does that x go? Well, that x remains in the denominator. And there you go. The x remains in the denominator. And now the denominator also, which was that, but I removed capital N over n from it. So that denominator turns into capital N minus 1, little n minus 1. True? And now I can cross out these x's. Cool. And what are we going to do next? Well, in this one, if we choose, notice, let's see, x begins with 0, right? The lower limit of summation begins with 0. So if I actually change that to k equals 1, actually let me show you this so it's not confusing. Let's go back up here where we did this. When x is 0, our first term in the expansion of the series will be 0, wouldn't it? Right, because you're multiplying 0 times something. So the first term of the series is 0, and then I can write it plus sigma x equals 1 to n of the latter part, right? X, that is, whatever is here, x times that fraction. So going off of this, what I have, I can actually change the index of summation as x equals 1 now. Okay, so in other words, I counted the first term in the expansion to be 0. We don't need that, so we start from x equals 1. Okay, we need to do that, otherwise this doesn't make sense, right? We're going to be getting a negative number. All right, and now this is good. So what is our next step? Next step, let's do this. Let's write this as little n, and then we have cap k over capital N. Okay. So we have that. And then I'm going to change my index of summation. Okay, we're going to let w be x minus 1. Okay, we're going to make that substitution. So if w is x minus 1, then if when x is 1, w becomes 0, right? When x is 1, w becomes 0. So that means I can write this as sigma w from 0 to n minus 1. And all I've done here is I shifted my series, right? Starts from 1 to n, goes from 1 to n. There are n terms in this series. So if you go from 0 to n minus 1, there's still n terms in this series. So I'm just shifting them, right? Using this new variable. And what do I need to do in the numerator now? So that's going to be k minus 1, right? And instead of x minus 1, I have my new variable, call it w, right? And then I can write the n minus k as n minus 1 minus k plus 1. So I added and subtracted 1 there. And instead of n minus x now, because remember x minus 1 is w, that's going to be n minus 1 minus w, right? And then divided by the denominator, which is cap n minus 1, little n minus 1. Okay, so we got that one. Now in this expression, let's see, what are we going to do next? We can actually bring the denominator out, right? So remember, in front I have n capital K over capital N bringing the denominator out, right? Because it doesn't depend on the index of summation. So that's going to be 1 over n minus 1, n minus 1, right? We have that times now the sum. Okay, and this is going to be the sum again, w0 to n of just the numerator. This time I only have the numerator. N minus 1 minus k plus 1, n minus 1 minus w. Okay. Now we can rewrite now this numerator that I just arrived at. This expression, we can rewrite it using the generalization that we had. Remember this one? This generalization, what we did here? So if you go through that change, we're going to rewrite the series using the right hand side of that generalized version. So this is going to be nk over capital N, and then times 1 over n minus 1 over n minus 1. And here's where I'm making an exchange for what you call it, for the summation. The right hand side is going to be when you just add those two items, right? So it's going to be the combination of k minus 1 plus n minus 1 minus k plus 1 over simply n minus 1. There we go, minus w plus w, if you will. But that's just going to be n minus 1. And this is going to be n k over n, 1 over n minus 1, n minus 1. And the right hand side, of course, now I can combine, and it combines into n minus 1 over n minus 1, right? That's using that generalization. So that was the key in doing this. Now these two cross out, and we simply have nk over n, and that's going to be the mean of the hypergeometric distribution. Boy, a lot of work just to get the mean out of that, right? Very complicated. And again, the complication is due to the factorial portion of it. All right, so hopefully you can follow all of this. So we're done with the mean. Now we want to find the variance. Okay. Now, using similar work, I'm not going to put so much detail in this one now as I did before. You can, now that you've seen it, you can verify some of these steps. But let's do the variance now. Okay, so we're looking at the variance of random variable x. That would be sigma squared x. So to that goal. Now to find the variance, we're going to start by this expected value of x minus 1. Okay, so that expectation, by definition of expectation, that's going to be sum from 0 to n of x times x minus 1, right? And then times the probability distribution. That was not k choose n, it was k choose x. And then that's capital N minus k choose n minus x divided by n choose n, right? Now this is not the definition of variance, that's just, I want to find that expectation. So this expectation is now going to be n using ways that we did before. Okay, in other words, This time I want to get xx minus 1 out. Notice when x is 0, the sigma, the summation, let me do this. The summation actually goes like this. When x is 0, it's a 0. When x is 1, this part is 0, right? 1 times 0 is 0. So really the meaningful non-zero terms begin when sigma is 2 actually, right? So this is like x equals 2 to n, right? 2 to n of x minus 1, and then the factorial, the combinatoric stuff, n minus k over n minus x divided by n choose n, right? Okay, so this is going to be n minus 1, and then we go k minus 1 over n minus 1, and then the sum x equals 2. Remember we counted 0 and 1, so x is going to go from 2 now to n, right? Of the fraction is going to be k minus 2 over x minus 2, and then n minus k over n minus x. We're not changing the latter part. The denominator, we work it just like we did for the mean. That's what it's gonna be. Okay. Now introducing the variable, if I let w this time be x minus 2. Okay, so when x is 2, x equal 2 implies w is 0, right? So this is gonna become n minus 1, k minus 1 all over n minus 1 times the sum. W goes from 0 to n minus 2 now, right? Of k minus 2 w, and then I can work the second one as n minus 2 negative m plus 2, and this would be n minus x minus w, right? All of that divided by n minus 2, little n minus 2. Okay. And now I can simplify this one, right? So this is going to become n minus 1, and then k times k minus 1. Again, by the same reason as we did for the mean, using the generalized series that I derived earlier in this video. That's going to be 1 over, bring the denominator out, n minus 2, n minus 2. And the sum of what you see in the numerator again, that sum is going to be k minus 2 plus n, right? That's k minus 2, and then the top portion of the next expression, plus n minus 2 minus m plus 2. The denominator is going to be n minus x, and or actually n minus 2 here, right? Sorry, it's going to be n minus 2 up here. Sorry about that. That's going to be n minus 2. Negative w plus w. Okay. So please correct this one. Make sure. Yeah. And it's good. So this is going to be n minus 1, k minus 1 over n minus 1 times 1 over n minus 2 times, now working this this expression, we're going to get n minus 2, little n minus 2. And of course, those end up being the same. And we have the formula for the variance. Well, not quite variance, sorry. For the expected value x times x minus 1. It's going to be n minus 1, k minus 1, divided by n minus 1. Right? There. That's what that's going to be. Now, let's actually find the variance. By definition, the variance of x is expected value of x squared minus expected value of x quantity squared. Okay, and this is going to be, now we can rewrite this expectation as expected value of x times x minus 1, let's go x plus 1. Actually, no, x minus 1. No, x minus 1 plus expected value of x minus the expected value of x squared. Okay. Now the expected value of x minus 1 is the one we just did, right? So that's going to be n minus 1 k minus 1 divided by n minus 1, right? We just showed that one, plus the expected value is going to be n k over capital N. We did that earlier also. And then you square this. You get n squared k squared over cap n squared. Okay. Now in this expression, I'm going to, they all have n, little n in common. They all have k in common, all fractions, and they all have a capital N in the denominator in common. So I'm just going to go n capital K over cap n. And that's going to make it n minus 1, k minus 1 over n minus 1, plus everything in the middle fraction is removed, so that's just 1, minus nk over n. Okay. And next step, so we have nk over n, and then we're going to choose the LCD, which is going to be n minus 1, and that's going to give me little n minus 1 times k minus 1, and of course times capital N to build it up to the LCD, plus n minus 1 negative n k, right? Times n minus 1. All right. Now we can actually simplify these, right? Let's see. So the upfront fraction is nk over capital N. Okay, now I'm working inside the bracket. Here's the denominator, n minus 1, right? Now in the numerator, when we distribute, we're going to get capital N k negative capital N negative capital N k plus n, right, when we FOIL them, plus n squared minus n, that's just distributing the middle one, and distributing the last binomial, we get negative n k minus times negative becomes positive nk. Okay, and then let's see if we can simplify this expression. n and k, those are opposites, they add to 0. And then what else? Cap n, little n, those add to zeros, right? And let's see, so I still have 1, 2, those 3 expressions, right? And let's see. Let's factor inside the bracket by grouping. Okay, so in order to do that, I'm going to group my, what you call it, cap n, little n, and n squared as my group, and then nk, capital NK, little n, k as another group. Okay, so first my nks. If I factor a negative k out, okay, I'm looking at this one and this one, factor negative k out, so that's going to give me what? Capital N minus n, right? And then factor an n from the other two group, from this one and this one, factor an n out, so I get n, capital N minus n. Okay, let me tidy up these things. There you go. Hopefully you can see better now. All right, so that's grouping them. Now you recognize the common binomial factor in the numerator, right? So I can factor it. This becomes nk over n, and then the factored form is n minus n times n minus k all over n minus 1, right? And there you have this one. So that is the variance. Boy, not for the faint of heart, right? And that is the variance of what you call it, the hypergeometric probability distribution. Now, if you recall the variance of a binomial, remember for the binomial, this is just on the side now, we're done with what we wanted to do, but for the binomial, the variance was np 1 minus p, right? Okay, so if p in that binomial expression, if you let p be m over n, so in the hypergeometric probability distribution, the ratio of cap m, or actually, sorry, I'm using k here, k to n, then from this, the mean, which is n capital K over n, becomes np, right? This was the mean of the hypergeometric. So notice it approaches the mean of the binomial, right? And in terms of the variances, if you look at the variance sigma squared h for hypergeometric, we said that's going to be nk over capital N times n minus k divided by n, and then n minus n divided by n minus 1. I went ahead and split these into product of two fractions. That's all I did. Okay, and for a reason, because remember k over n is p, so that's going to be just np, right? And the term, this one, is going to be 1 minus k over n. That's 1 minus p, right? np 1 minus p, and then of course we have it times this last expression, cap n minus little n over cap n minus 1. Okay, so we can kind of see now the variance of binomial in there somehow. Isn't that cool? So the hypergeometric variance is going to be that of the binomial times a factor n minus n over n minus 1, right? So that's interesting. Now, if you let both m and n, if you let m and n approach infinity and become very large, then I'm sorry, not m but k and n approaching infinity, then it turns out that this limit, right, then the limit as n approaches infinity of cap n minus n over cap n minus 1 is 1. So what that means is that the variance of hypergeometric approaches the variance of the binomial for very large n. Okay, and in fact that's we can conclude that the hypergeometric probability distribution approaches the binomial distribution, and hence this is the reason we use normal approximation for sampling without replacement for large populations, right? This is the justification for that, because the hypergeometric does approach binomial. Okay, so, and that means replacement or without replacement makes no difference when population is large, and of course the ratio of little n to capital N must be greater than 5%. So we are done with this video. This was very drawn out because we covered a lot of grounds and they were not again trivial. We started by definition of a hypergeometric experiment. We went on the side, looked at hypergeometric series and the rationale for naming hypergeometric distribution. Wrote the probability distribution, and this was very important observation we made in order to arrive at the formula for the mean and ultimately the variance of a hypergeometric distribution. And with that, we are done with this lecture.